Good day to you. This is a video on how to do problem 2.24 from the book David J. Griffiths Introduction to Electrodynamics. This is the 8th edition, so if you don't have the same problem as I do, check to make sure that you have the right edition. Again, this is 2.24, 8th edition of Introduction to Electrodynamics by David J. Griffiths. So, first out, the problem, let me just read out the problem so we all know where we're at. It just says, for the configuration of problem 2.16, find the potential difference between a point on the axis and a point on the outer cylinder. Note that this is not necessary to commit yourself to a particular reference point if you use equation 2.22. I have equation 2.22 written out right here, where voltage at B minus the voltage at A, or potential, sorry, is equal to the negative integral from A to B of the electric field of dl. If you've already done problem 2.16, you can go ahead and skip on to the part where I do 2.24. However, if you have not done problem 2.16, just stay tuned because I'll get started on that now. All right, so we're gonna head over to problem 2.16. If you've already done this, go ahead and skip. But as of right now, let's go read the problem. To scroll in, give me 1 second. So problem 2.16 or 2.16, sorry, states a long coaxial cable carries a uniform volume charge density rho on the inner cylinder of radius A, right here, and a uniform surface charge density sigma on the outer cylindrical shell radius B. The surface charge is negative and is of just the right magnitude that the cable as a whole is electrically neutral. Find the electric field in each of the three regions. 1, inside cylinder A. 2, where S is going to be greater than A but less than B, so in this little region right here. And lastly, the region outside, S greater than B, outside here. All right, so first off, here's what we know. We have the cylinder. Here's how I've drawn it out. And I'm actually gonna draw this. It's supposed to be in the Z direction, but as of now, I'll label this direction coming out of the cable in the L hat direction. All right, it's just gonna be the Z direction, so as if that's where it's standing up. But because we have it on the side, it's gonna come in useful later when we integrate. Again, I've drawn these plus signs right here to indicate that the inner cable, A, has a positive volume charge to it, whereas cable B has a uniform surface charge density sigma to it. So I've drawn these little negatives out here so we can see what's happening. So we also know that the area between, or the volume between A and B, so this area and volume right here, there's really no charge there. There is an electric field there, but that's going to be coming from cable A. Cable B has no charge kind of inside of it, like in the little atoms of it, only inside it. Cable B will have that surface charge above it. So outside of it, it seems electrically neutral. So first off, let's see what we gotta find. The electric field of the first part, as less than A, as less than A, make sure we're right in there. The second part, A is less than S, but S is less than B. Lastly, S greater than B. All right. Now the equation that we're going to use is equation 2.13 in the book. And this equation is a closed integral of the electric field dot dA, both vectors, equal 1 over epsilon naught and the charge enclosed, or the Q enclosed, so ENC. All right, so from this equation, we also have Q enclosed is going to equal the integral of rho, the volume charge density, of d tau prime. The reason why we put that prime is we know that this integral, it's going to be a volume integral. It's going to be the volume integral of our source, of what's going to give it charge. So when we look at this area here later, this area between A and B, and we evaluate, the electric field with the charge enclosed, the volume of the charge enclosed will only be this cable A, because inside cable B, there's no charge in here. It's going to be technically like a neutral cable, but the charge enclosed, the Q enclosed, will only talk about this cable A. So when we integrate that volume later, we only consider the bounds of what cable A is and not where we are integrating or where we're evaluating. Sorry, there we go. All right, so let's get started. First with I, right? S less than A. We look at this equation, E dot dA equals 1 over epsilon Q enclosed. Now, when I make our Gaussian surface, which is kind of like a surface of where we're going to be evaluating, for S less than A, I'm going to just draw it right in the middle. So right here. Of course, this surface isn't just right there. We're evaluating between 0 all the way up to A. So right from the axis all the way to cable A. Thing is, this might look like a cylinder, but remember, when we're talking about dA here of the electric field, and we have this Gaussian surface, these are my notes. This Gaussian surface that we have made, so let's say my arm is cable A. And my Gaussian surface, oh, wait, my bad. The Gaussian surface will be inside. I don't have anything to enclose this. So this Gaussian surface right here, just like this, when we talk about dA, it's going to be talking about this area of the cylinder, right? There's no volume inside of it other than just air or whatever cable A is. But our dA is going to be this all around, and not over here, all around here. So we are going to have an integral. And this, oh, I also forgot. This will be length L for now. And every Gaussian surface that we make, one at inside of A, one in the middle of A and B, and one outside of B, they will all have the length L. Just so that we have the same thing for everything. All right. So first off, we have L equals 0 to L, just from 0 to L. So we just have this as a reference point right here. Just consider this as L equals 0. And over here, L equals L. All right. I'll erase that later so we do the other Gaussian surface. But we will also have phi, right? Because for this to have a surface in an area, inside this, we have the length of the cylinder or Gaussian surface. And then we also have this side so that we can see that surface, a two-dimensional plot. Phi equals 0 to 2 pi because we will be going all the way around. E dot, so dl first, and then it's going to be S d phi. Don't forget the S there. The S is what makes it important because the S allows us to know where we are on that coordinate system, right? If we were using cylindrical coordinates and I just gave you, we are at angle pi on the phi scale, right? Now you might know which direction pi is, but you don't know where exactly you are because you don't have how far you are from the axis. If I just give you that angle pi, you might look in that direction, but you don't know where to go if I don't give you how far out to go. So that S is definitely crucial in there, right? Right side is just 1 over epsilon naught Q enclosed, and we'll work on that right side later. So first off, this seems very simple to do. There's no ds here, so we can take E and S out. 0 to L dl, 0 to 2 pi d phi. All right, and that will come out to E S 2 pi L. And you can write this in any way that you want, but as long as those variables are there. Now let's work on that right side, right? 1 over epsilon naught Q enclosed equals 1 over epsilon naught integral of rho d tau prime. And because our Gaussian surface here, so this is going to be the charge enclosed. So wherever we are, there will always be charge enclosed all the way up to A. So even as we go further and further out all the way to the edge of the cable A, we are going to have new charge enclosed available to us. So d tau is going to be kind of like equals both dl s d phi, can't forget that, and lastly, of course, ds itself, because this is going to be a volume integral. But our limits are going to be a little different. Equals 1 over epsilon naught. So we actually can take rho out because there's no L, phi, or S inside rho. And rho itself is a uniform volume charge density, so it's just a constant. We can take that out. So let's start with dl first. So easy, 0 to L, dl. All right. And then we got d phi, 0 to 2 pi, d phi, and then s ds. So we can take that s out and put it over here, s ds. And s ds is actually going to go from 0 to s instead of a, because if we were to go from a and the left side only went to s, then if we were evaluating right here, let's say es, right, and we just plug this random like a over 2 for s, but if we left a over here, then we would be evaluating all the charge all the way up to the cable. We only want the charge enclosed, so only up to s. All right, we have this side, we have that side. Let's integrate. Equals rho over epsilon naught, 0 to L dl, pretty simple. L, pretty sure. I always like to gaslight myself into thinking I'm wrong with the most simple integrals. All right, 0 to pi. Oh, why did I put d pi there? My bad. That's going to be d phi. That's my fault there. So if you got that mistake, good for you. If you were a little confused, that is my fault. Instead of d pi, that is d phi. All right, 0 to 2 pi of d phi, nothing in there, 2 pi. Pretty simple. Over here, 0 to s ds. So that's going to turn into, I'm going to write over here, s squared over 2 from 0 to s. Of course, 0 plugged in there is just 0, so we just have this as s squared over 2. We can cancel out the 2 here. And we have this equal to PL pi s squared, or P, not P, rho L s squared. I forgot the pi. Rho L pi s squared. 2's cancel over epsilon naught. Pi's cancel out here. L cancels out here. S cancels out with the power. And the 2 goes on to the other side, so we have an electric field equals rho L S over, yeah, I'm pretty sure, 2 epsilon naught. All right, let me check my notes to make sure I am good to go. Rho S, oh, my bad. I forgot I canceled out the L's. Equals rho S 2 epsilon naught in the s direction, because we're putting this as a vector. Electric field is always a vector. Remember that. It's going to be in the s direction because from this cable, it's going to be emitting out of the cable. All right. So for I, I'll just put E1 equals rho S over 2 epsilon naught S hat. Now we have our first area. All right, let's do second area, or second volume, I guess, where A is less than S and S is less than B. All right, so this area right here. We can easily do the left side again since we already have it from the first part, right? Because it's going to be the same thing. So now our Gaussian surface is going to be a little different. We have the same length. That's why I'm going to keep it as. But now our Gaussian surface is going to go all the way around. Sorry, that was really bad. But yeah, it's going to be right there. It's going to be outside of A, inside of B. Now, as you can see here, the charge enclosed is only going to be cable A. There's no charge within this area between A and B. Remember that. So now we also know that the charge enclosed is only going to go up to A. However, E dl, L stays the same, S d phi stays the same because S is just kind of something that we put in there to hold our values. So the left side of the equation of equation 2.13, E dot dA, or the integral of E dot dA, stays the same as E S 2 pi L, all right? But the right side equals 1 over epsilon naught Q enclosed equals 1 over epsilon naught integral of rho d tau prime. Integration is going to be between dl, s d phi again, and ds, just like last part. But integration limits, let's see here, 1 over epsilon naught. We can put rho on the outside again, just like we did last time. Let's start with dl, 0 to L, dl. Because nothing's changed here. It's still from 0 to L. Our Gaussian surface will always be the same way, 0 to L. We go over to phi, 0 to 2 pi d phi. That's not d pi again like I did last time. That's d phi. All right, d phi still goes in a whole circle. Easy. However, our charge enclosed for S ds, our S now doesn't just go to S. It's going to go only all the way to A. All right, so we can just have it as 0 to A. Here we go. So on the left side of the equation, or the right side, sorry, yes, 2 pi L will equal, so that's going to be L right there. That's going to be 2 pi again. And on this right here, S ds, S squared over 2 from 0 to A. 0 plug in, so it's just going to be A squared over 2. So now we got A squared over 2 on this side. 2 cancels out with that one. We still have these to worry about. We have that, we have that, we have A squared. So over here, run out of room here. Part 2 continued. You got ES 2 pi L equal 1 over epsilon naught rho. Oh, there we go. Sorry about that. That should be better. I think over here. Okay, yeah, I'm better now. ES 2 pi L equals 1 over epsilon rho. And right earlier we had L, we had 2 pi, and we had A squared over 2. 2 cancels out here. Pi can cancel on this side. L can cancel out here. 2 will go to the other side. S will go to the other side. So we have E equals rho. Let's see, anything in the top? A squared over S2 epsilon naught. We'll put 2S epsilon naught. So we have the 2 in the front. All right. Make sure PA squared over 2 epsilon naught S vector S hat. All right. There we go. This is going to be section 2. All right. So we have, let me write it over here. I. You have the electric field as E1 equals rho S over 2 epsilon naught S hat. We have section 2. So this is S less than A. This is A less than S less than B. E equals rho A squared over 2S epsilon naught S hat. And now lastly, we have section 3. So let's go back to the picture. And I got, this one's gonna be the toughest one of all. So, cable is electrically neutral as a whole. And that's what's stated in the problem. If that's the case, electric field 3, so outside, so this is 2, E3 equals 0. That's all you gotta do. Just like that. Because it stays in the problem. So sometimes I will psych myself out during these tests and quizzes, but physics people like to mess around with each other. So if you read the question a little carefully, you might see something very simple to get you some points. All right, this is section 2.16. I will stop this video here to make sure I did the video correctly and start the video again for 2.24, so there will be a small cut. All right, so I'll put it over here for the next part of the video. We have electric field of inside cable A, electric field between cable A and cable B, and electric field outside the cable. All right, see you in the next part of the problem. Welcome to the second half of the video where we actually evaluate or do the problem 2.24 in David J. Griffiths Electrodynamics, all right, or Introduction to Electrodynamics. From problem 2.16, we had gotten the electric field of all 3 regions of this coaxial cable. So there's that cable A, cable B, and outside cable, or all 2 cables. The electric field inside cable A is going to be right here, rho S over 2 epsilon naught. That's a really bad epsilon in the S hat direction. Epsilon, or electric field 2, which is this area or volume between cable A and cable B. Or, yeah, basically it is cable B. But anything between the edge of cable B up to the edge of cable A, that is section 2. And we have the electric field of rho A squared over 2 epsilon S in the S hat direction. And lastly, we have that the electric field 3, or region 3 of the outside of the cable, is just 0. Because the question was labeled, or the question was stated in such a way that it said the entire cable is electrically neutral as a whole. So, from that inferment, the electric field outside is just 0. All right, now problem 2.24 has us evaluate the potential difference between a point on the axis. So, let's draw that axis. So this, technically, if we had the cylinder in the upright direction, this is basically just kind of the z hat direction, and anything phi related will be along that cylinder as it turns. All right. So note that it is not necessary to commit to yourself to a particular reference point if you use equation 2.22. VB minus VA equals negative integral of A to B E dot dl. All right, so we have, however, the thing is, we have 3 different electric fields here. All right, so let's see. First part, you gotta find a point on the axis to a point on the outer cylinder. So let's just go from here to here. Why not, right? Very simple. Let's get this started. Oh, sorry. Give me 1 second. Want to make sure we're still in frame. All right. So VB, we'll still leave that as B because that's going to be the outside ring or outside cylinder. V of B. However, it also says potential difference between a point on the axis and a point on the outer cylinder. So our VA will actually be just 0 because that will be right there, 0 on the axis. Equals negative. So instead of A right there, it's going to be 0 to B E dot dl. But we do have to split this up because the electric field is different at each region. So we can actually set this to from 0 to A first. E1. Oh, that's not an A. 1 dot dl plus, well, this actually kind of turns out to a minus because the equation is a minus, minus a to b e2 dot dl. All right. So as you can see here, even though this is just a to b and we have 0 to b here, we changed it into two different parts and we kept that negative sign because it's just part of the same integral. All right. 0 to a first and then a to b. All right, so let's get started with this first part integral, right? So this is going to be I and this is going to be, or 2, I, double I. Sometimes I just say double I. All right, let's do I. All right, negative 0 to a e dot dl. And dl is just a simple integration from 0 to l. All right, so 0 to a, we have rho s 2 epsilon naught, keeping that s hat direction. So this is actually, instead of being dl hat, because the length or the line path integral that we're taking is from here to here. And in which direction is this? That's right. It's going to be in the ds direction. So dl, from the last problem in 2.16, we told us that L was from here to here in this way. But this part's a little different. This is just the line that we're going to be taking, or the path that we're going to be taking. And because the path is simply a line straight out, it's just in the S direction. All right. So this is going to turn into ds. And that makes it that much more interesting. Oh, why did I put that there? All right. Now, as you can see, integrate p. Is that a ds? Nah, 2 epsilon naught. We can take those out. This will equal to negative rho over 2 epsilon naught integral 0 to a of s ds. I need to make sure that I'm not tricking myself into how simple of an integral that is. But we all know that s, the integral of s, turns into s squared over 2. And when it's from 0 to a, I need to take very baby steps here because there's one time, anecdote, on a test, I wrote the integral of s is equal to s. And that's not the case. The integral of s is s squared over 2, especially with respect to s, of course. So I need to make sure every time, because sometimes I do mess this up. S squared over 2 from 0 to a, that will just give you a squared over 2. Make sure that's good. All right. A squared over 2. So now we have the first part as I. Let's put it as I. All right. Equals. Don't forget the negative in there. Rho 2 epsilon naught. Rho. Negative rho. A squared over 4 epsilon naught now because we have this 2 here over 4 epsilon naught. Just to make sure, I will be checking my answer. Rho A. All right, sounds good. So we have that part. I equals negative rho A squared over 4 epsilon naught. I'm going to circle that so I don't forget where it is. We work on part 2. All right. So it's going to be the integral a to b e2. So rho a squared over 2 epsilon naught s ds. All right. And since it's in ds, we can take out all these other variables that aren't part of the integral. Equals negative rho over rho a squared 2 epsilon naught a to b 1 over s ds. All right. Now we all know what that means. This is equal to, just right here, natural log of s evaluated from a to b. We all know that this comes out to ln of b minus ln of a, which equals natural log of b over a. All right. So we got that for there, and we can put that right back in. So for I will equal, don't forget the negative, negative rho a squared over 2 epsilon naught natural log of B over A. All right, we circle that. All right, so now just on this, VB minus V0, or potential of B minus potential of the axis, is going to equal I plus double I, right? Because we already have this minus in there. We already put that minus right here. Oh, my bad. Minus right here, and the minus right here. All right, so technically we are just setting this to be, so these are variables, I and double I, B of B minus B of 0 equals I plus I. All right, so let's add these bad boys together. Equals negative rho A squared over 4 epsilon naught. So this looks very similar to this right here, but because this has a 4 in the denominator and this only has a 2, I'm just going to apply this by 2 over 2. So we can actually get minus 2 rho A squared over 4 epsilon naught natural log of B over A. All right. So that makes it easier to factor some stuff out, all right? So V of B minus V of 0 equals, let's take all these out. Let's take it as a negative. So rho is in both, A squared is in both, and 4 epsilon naught is in both. And we can take that out to be 1 plus 2 natural log of B over A. All right. Sorry for the slant. So that's the answer right there. The potential difference between something on the outer edge of the cylinder to the center, or the axis, is going to be rho A squared over 4 epsilon naught times 1 plus 2 natural log of B over A. All right. Rho is the volume charge density of A. A is just the radius of cable A. Epsilon naught, B is going to be the radius of the bigger cable, cable B, and A again. And there you have it.